Surface tension transfer, or STT, is a proprietary Lincoln electric process. Spatter levels are very low, even when welding with CO2 in the short-circuiting mode. Heat input is optimized. STT, a fast follow process, permits high travel speeds and precise control of the bead size and shape. It is particularly efficient for automated welding of thin-gauge steel. This process provides good penetration. The weld puddle is tightly controllable because of the low heat input and controlled weld metal transfer. Difficult applications like nickel alloys and open root welding are easily accomplished with the smooth arc. This waveform schematic depicts very rapid changes in current. The STT machine responds to changes in and the condition of the welding arc. Current is raised and lowered to transfer molten droplets cleanly. Normally violent short arc or globular transfer processes are stabilized. Here's STT welding with CO2 shielding gas. There's very low spatter. The arc is well controlled. If this were a normal short-circuiting process, there would be higher spatter levels. With the STT process, droplet size is tightly controlled. Transfer to the workpiece is clean. Compare this to the large droplets of globular transfer. When an abnormality occurs, the high-speed current control of the STT power source adapts to transfer droplets smoothly. Let's break down the waveform for a better understanding of waveform control technology. The STT provides a very specific waveform control that instantaneously reacts to the arc during short arc welding. At the initial shorting of the electrode, the STT process reduces the current or energy to minimize spatter. Next, a high current is applied, accelerating the molten metal transfer to the weld puddle. Prior to fuse separation, the current is reduced in millionths of a second to reduce the explosive nature of the molten metal transfer. A plasma boost current is then imposed on the arc. It melts the electrode back. This reduces spatter and fume generation. The arc current is then reduced to the background level in a controlled manner, reducing weld puddle agitation. It is the instantaneous control over the current that eliminates the highly violent and explosive energy of short arc MIG welding. Now, what if we applied waveform control logic to more than just short arc MIG? We would have a precise control of the arc through a very broad wire feed speed range. That is the major benefit of using the Lincoln PowerWave pulsed arc welding process. The process allows wire feed speeds ranging from 50 to 1200 inches per minute, and it's virtually spatter-free across the entire range. With precise control of arc dynamics, the PowerWave can be used as a fast-follow process at high travel speeds, or it can be run as a high deposition rate fast-fill process. Precise control of the output waveform varies the arc characteristics. Weld out of position easily with the gas metal arc PowerWave process. The arc is very stable. The PowerWave is very effective for welding steel, stainless, aluminum, and most alloys. The pulsed spray arc is as stable as a converted spray arc. The pulsing process transfers small droplets directly through the arc. One droplet during each pulse. As the wire is advanced, the current pulses and transfers the next droplet. Let's look at the pulse process at a higher wire feed speed. This is not pure pulse welding, rather an intermittent spray arc welding. The PowerWave power source has waveform control technology. It provides a very fast front edge on the pulse, transferring the droplets quickly. The back edge of the pulse falls at a controlled rate to add the heat input needed to wet the droplet into the puddle. Pulse spray is stable at a wide range of wire feed speeds. The process offers more advantages at both higher and lower wire feed speeds than converted axial spray. But with the waveform control technology processes, there is much more processing versatility and capability. More choices are available when adjusting the arc length of these processes. Controlling the welding process depends on how we change the instantaneous parameters together to achieve the most stable arc. The magic of the Power Wave is that we have pre-programmed a computer to help you set welding procedures. We took a Power Wave synergic power source and loaded it with 045 L56 wire and used a 90-10 argon CO2 blend. We started at 100 inches per minute wire feed speed and increased the procedure to 650 inches per minute. The synergic property of the Power Wave sets the correct arc length for each wire feed speed. The CV mode is first. Note the definite transitions between the short-circuiting, the globular, and spray arc transfer ranges. The differences between the three transfer modes are significant. At the high end of the spray arc range, the arc begins to rotate and eventually becomes unstable. Now, let's run the Power Wave in the pulsed mode through the same 100 to 650 inches per minute wire feed speed range. The spray arc transfer mode is maintained across the entire range. No spatter occurs at any point along the range. At the high end, the arc remains stable and does not rotate. Pulse generates a controlled heat input to control distortion and burn-through and to aid in out-of-position welding. The occasional visible spatter from the pulse process does not stick to the workpiece or torch. The small droplets do not contain enough energy to fuse to the workpiece. The Power Wave welding procedures provide enough heat input to make a sound weld while minimizing spatter by controlling the weld puddle.